students. So yesterday we were looking into the concepts of or in our previous class we were looking into the concepts of surface integral and circulation of a function around a given curve and things like that. So today we will continue practicing those examples, and then if time permits then we will move on to our next topic, which is basically Green's function, as in Green's theorem actually. Green's function is actually in some other topics. So we will look into Green's theorem in the vector calculus context. So first of all, let's start with our example on circulation actually. So our first example is find the circulation of f around the curve C, where f is equals to yi zj plus xk, and C is the circle x square plus y square equals to 1 and z equals to 0. So basically here we have to find out the circulation of this function f around a curve C, where we have the given function f x y z equals to this. So of course f is a function of x, y and z. So C is the circle given by x square plus y square equals to 1 and z equals to 0. So basically our curve is in the xy plane, and the given equation of the curve is basically a circle. So by definition we know that, so by definition of circulation, so by definition the circulation, so since it is a circle which is a simple closed curve, so any line integral along that simple closed curve will be circulation. So by definition the circulation of f around C is this notation, f dot dr. So this can be written as where r is basically xi plus yj plus zk. We know that r is always given by this way, and therefore from here we will have dr is equals to dxi plus dyj plus dzk. Right now here if I write integral over the curve C, yi plus zj plus xk, and then this can be written as dxi plus dyj plus dzk. Now since we are in the xy plane, so z is 0 and dz is 0. So if I substitute z is 0 here and dz 0 here, then this will lead to integral over C. This is 0, this is 0. So ultimately we will have y dx, because on C, since on C z is 0 and this implies dz is also 0. So we will basically substitute z equals to 0 here and dz equals to 0 here. So we will end up with integral over C y dx. Now if I substitute x equals to cos theta and y equals to sin theta, so this is basically integral over the curve C. So in this case the parameter theta would vary from 0 to 2 pi. I am substituting x equals to cos theta, y equals to sin theta. So this is sin theta, and then if x equals to cos theta, then dx is minus of sin theta d theta. So this will be minus of sin square theta d theta. So I can adjust a minus half here, and then this will be theta running from 0 to 2 pi 2 sin square theta, and then this can be written as 1 minus cos 2 theta, 1 minus cos 2 theta, and if we integrate d theta, then this will be minus half, this will be theta minus sin 2 theta by 2 integral from 0 to 2 pi. So sine 2 pi is 0, sine 4 pi is 0, sine 0 is 0. So this will be ultimately minus of 2 pi by 2. So answer is minus pi. So this is the required circulation of this function f around this curve C given by this circle. So circle is a simple closed curve. So the line integral will be a circulation. So this is how we calculate the circulation of the function f. All right. Now we will continue with our examples on surface integral. So let me write an example. Let me write a problem here. So evaluate integral over the surface S f dot n ds, where f of x y z is given by z I x j minus of 3 y square z k, where S is the surface of the cylinder, x square plus y square equals to 6 included in the first octant z equals to 0 and z equals to 5. So basically x square plus y square equals to 16. So that's a circle, and then you have z equals to 0 and z equals to 5. So it is a cylinder. Now if you consider the part which is included in the first octant, that means the circle in the first octant, and the length z equals to 0 to z equals to 5 at the I mean like the height of that cylinder. So whatever lies in the first octant of that cylinder, so that's the surface S, and our given vector function f is this one. So first of all, if we have a given vector function f, so from there we have to, and if we have the surface S, then from there we have to find out the normal n. So a vector normal to the surface, we if you remember, then yesterday we basically calculated the gradient of this this x square plus y square minus 16. That's our given surface. So a vector normal to the surface S is given by gradient of x square plus y square minus 16, and this will be 2 times del x. So this is basically x I plus y j. Yes. So this is the required normal, and from here the unit normal. Therefore the unit normal, therefore n cap, a unit normal, basically unit normal at any point on S. At any point on S will be given by gradient of, let us say this one was our phi. So if this one was our phi, so grad phi divided by mod of grad phi. So this is 2 x I plus y j, and divided by x square plus y square. Now x square plus y square is basically 16. So this will be 2 x I plus y j divided by 4. So this is x I plus y j divided by 2. So this is our unit normal n. Now since we have a cylinder which is whose base is x square plus y square equals to 16 and height is 5. So we take a projection either on xz plane or yz plane. So if we take the projection on xz plane, so we have in surface integral over S f dot n ds, or let us say n cap. So this can be written as surface integral over S f dot n, and if I take the projection on xz plane, so dx dz, and then dot product will be n dot j, right. So this is our required dot product, where r is the, and this one can be, let us write as S1. So where S1 is the projection, or let us call it as R. So, S for the surface and R for the region. So, where R is the region, where R is the projection of S on xz plane. So, that is the projection on xz plane, and we cannot take the projection. So, we cannot take the projection of S on xy plane, as the surface S is perpendicular to the xy plane. So, we simply cannot take the projection, because since the cylinder is perpendicular to xy plane. So, if we take the projection, then it will be just a circle. So, I mean we exclude that cylinder part here. So, that is why we take the projection either on xz plane or yz plane. So, that is that, and now our n is xi plus yj divided by 2. So, from here n dot j would be just y by 2, and n dot j mod will be simply y by 2, right. And f dot n is basically our f is given by zi plus xj minus this. So, when we take the dot product, so the k component is 0. So, that will be 0, and therefore, this will be xz plus xy by 2, right. So, this will be xz plus xy by 2, and now xz plus xy by 2, right. So, we have this here. So, this is 4. Okay. So, here I am getting 4. So, 2 to did I do this calculation correctly? So, this will be 4 x square 4 y square. So, this will be a square root of 4. So, that means 2. So, so there will not be any 2 here. So, just xi plus yj, and that means here we will have simply y. So, this will be just y. I am sorry. So, this will be just y, and then here we will have xz plus xy. So, when we take the dot product, now we substitute all these values here. So, our required surface integral S equals to f dot n ds, which is equals to integral over region R. F dot n is xz plus xy, and this one will be dx dz, n dot j. So, n dot j is simply y. And now, if we take the projection on R, then this will be integral over the region R. Z will be running from 0 to 5, and x will be running from 0 to 4, xz plus xy. So, y will be 16 minus x square. Wait. So, this is here 4. So, this is 2, and this will be x square plus y square. So, here it will be 4, right? Yes. So, it will be 4 here, and then there will be a 4 here. So, y by 4, this is also y by 4, and this is y by 4. So, this will be by 4, and this is by 4, and next we will have xz plus 16 minus x square divided by y. So, y is also 16 minus x square dx dz. Now, this can be written as, if we simplify, then this will be written as z running from 0 to 5, x running from 0 to 4, right, in the xz plane, and this will be xz divided by 16 minus x square plus x dx dz. So, we did the separation. So, basically the partial fraction, and now we can integrate this very easily. So, we basically do the integration with respect to x first, and So, this one will be x square by 2, and this one will be, if we substitute this equals to z, so that will be just square root of z and all that. So, doing simplification from here is not complicated. So, we will basically at the end obtain 0 to 5 4z plus 8 times dz, which is equals to 90. So, this is the required surface integral. Yeah, so here there is a small mix up. So, it is just that here it will be x square plus y square, this 2 will come outside, and since x square plus y square equals to 16. So, it will be 2 times 4. So, 2 will get cancelled. So, we will obtain simply 4. Yeah, sorry about that mix up. And then when we take the dot product, so then this will be y by 4, and this will be x z plus x y by 4. So, ultimately they get cancelled. So, they really do not affect anything. It is just that yeah, we have to be a little bit careful. And now substituting y equals to 16 minus x square, and here also then we do the partial fraction, and then this is ultimately 19. So, this is how we calculate the surface integral of a given surface integral of a given function f, whose surface S is given by that circle and cylinder. So, that was another interesting example. We can consider another example on surface integral before we move to the Green's theorem. So, another example, evaluate where f is equals to yi 2xj minus zk on S, and S is the surface of the plane 2x plus y equals to 6 in the first octant. Cut off by the plane z equals to 4. So, here we have a given equation of the given how to say equation vector function actually, and S is the surface of the plane in the first octant cut off by the plane z equals to 4, right. So, that is the given equation of the surface. So, now first of all we will calculate the normal. So, a vector normal to the surface S is given by let us say n equals to gradient of 2x plus y minus 6. So, this is ultimately 2I plus j, and therefore, from here our unit normal is n by mod of n. So, this will be 2I plus j square root of 5, right. So, this is our required normal unit normal actually, and the given surface integral S can be written as. So, since we have to take a projection. So, in this case also we take the projection either on x z or y z plane. So, we cannot take the projection on x y plane because the surface S is perpendicular to the x y plane. So, here we take the surface integral and we take the projection. So, that is the region R where the projection will be f dot n, and ds will be dx dz divided by n dot j. So, now n is given in this fashion. So, n dot j would be 1 by square root of 5, right, and f dot n would be 2y plus 2x divided by square root of 5. The k component is 0. So, dot product after taking the dot product, the k component will not occur here. So, that is what we will get f dot n, and that is what we will get as n dot j. So, we substitute everything here. So, it will be let's say is our surface integral. So over the region R, f dot n is 2 square root of 2 by square root of 5 y plus x times so it is y plus x times 1 dx dz divided by 1 by square root of 5, right. So square root of 5 will get cancelled, and this will become 1 by 2 times integral over the region R y plus x dx dz. Now y can be written as over region R, y can be written as 6 minus x, right. So here, where is that? So our y is 6 minus 2x actually. So this is basically 6 minus 2x plus x times dx dz, since 2x plus y equals to 6, and now this will be 2 times integral over the region R 6 minus x times dx dz. Now x, if we take the projection on xz plane, then in xz plane basically y is 0. So x will vary from 0 to 3 and z will vary from 0 to 4. So I can write the integral as x varying from 0 to 3 and z varying from 0 to 4, 6 minus x dx dz. Here there is a 2, and we can integrate with respect to z first. So it will be 2 times 4, and then we integrate with respect to x. So this will be 6 minus x times dx, and so this will be 2 times 4, it is 6x minus x square by 3. So this is 6 times 3 minus 9 by 2. So ultimately it will be 108. So that's the required surface integral. So like this, you can practice many more examples where you have a given vector function. So you take the projection on x y plane, y z plane, or z x plane. You have to find out the normal n which is perpendicular to the surface, and then everything is just doing some simple calculation. So after doing the projection, you get to know what is the limit for x or y or z depending on your projection, and then just perform the integration. It's from then on onwards it will become very simple. So I will move to our next topic, because I think we have practiced enough examples on surface integral, and next we will move to our next topic, which is basically Green's theorem. So Green's theorem states that let R be a closed bounded domain or closed bounded region, in the x y plane whose boundary C consists of finitely many smooth curves. And let M and N be the continuous functions of x and y having continuous partial derivatives. Del m del y and del n del x in R. Then, so basically then surface integral over the region R del n del x minus del m del y dx dy is equals to circulation over the closed curve C m dx plus n dy, where the line integral, where the line integral being taken along the entire boundary C of R such that R is on the left side as one advances in the direction of integration. So, basically R is a closed bounded region in the x y plane, and suppose we have two functions m and n which are continuous functions of x and y, which has continuous partial derivatives del m del y and del n del x in R. Then if it has continuous partial derivatives, then we can write del n del x minus del m del y dx dy is equals to line integral over the curve C m dx plus n dy, where the line integral is taken in such a way that when you walk along this curve C, then your region R will always be on the left hand side. So, that means you always have a anti-clockwise direction. So, the way you are walking along the boundary C is such that the region R, which is being closed by the boundary by the curve C, is always on the left hand side. So, that means you always walk along along the anti-clockwise direction, and this is what this theorem says, and all you need to have is that m and n should have continuous partial derivatives of order 1, and then this identity would hold. So, we can actually verify this identity. It is also one of the important theorems in vector calculus, and we can be able to verify this by using some formulas and some calculus results. So, I will stop here for today, and in the next class we will work out one or two examples on Green's theorem, and we will see how it is being solved. So, thank you for your attention, and I look forward to you in your next class.